Next up, we have Jafar, who's going to talk about Falcor.
All right, thank you, Jared, for that super depressing talk. No, it's great. AS 2016 is going to be very, very cool. I'm actually on the committee myself. My name is Jafar Husain. I work with his colleague there on the committee, and there's lots of cool stuff, as you can see, coming in JavaScript. Today, I'm here to talk to you about Falcor. And really, if I was to convey to you what Falcor effectively is, it's the way to think about it is that every single user out there who's on a mobile phone or is using a web browser, they want to feel like the entire cloud is just sitting right there on their device. Oh, man. There we go. So Falcor allows you, as developers, to code that way. We as developers are kind of like magicians. We're like playing a little conjuring trick, right? When users try and go and access data, we go and grab it from the cloud and we hand it to them, and our job is kind of create the illusion that all the data is just sitting right there on their phone or however small that device is. So why is web development so challenging? Why are connected applications so challenging? Well, I think it starts to some degree with REST. How many people out there, out of curiosity, consider their API, their server API, to be RESTful? Okay, some hands. All right, fair enough. So when we think about the REST, I think we think about World Wide Web, right? I mean, REST was actually a set of architectural principles derived from what worked about the World Wide Web, right? So for those of us old enough to remember, modems that made bleepy noises back in the day with the World Wide Web, what do we think about it? We think of it as a big graph of resources, right? And we have a series of unique identifiers, URLs, and then we have a series of idempotent operations, get, put, and some non-idempotent operations, post. So the World Wide Web is great for a whole series of static resources that you just want to browse through. That's originally what the World Wide Web is for. So REST kind of makes a lot of sense for Netflix. So I work at Netflix, and we were looking at different models by which we might expose our data on the web. And REST kind of jumped out at us because Netflix is fundamentally a browsing problem, right? The World Wide Web works really well for browsing mostly static resources. And although our catalog changes pretty dynamically, within the length of, say, an individual user session for a Netflix user, our catalog's not changing all over the place. We want to benefit from things like caching, and REST is really good at caching. So we started down this road of REST. And so, first of all, we had pretty darn RESTful API, right? If you look at that API, it looks very, crisp, each individual resources. And then over time, our RESTful API kind of turned into like a not so RESTful API, as you'll see in a moment. And there's a reason for that. Here's an example of an individual Netflix resource, right? JSON, a small piece of JSON about a title. Now, that's one particular title. When you load up your Netflix homepage, well, I mean, if each one of those little titles was a resource, we might issue 30 HTTP requests on a phone. That's not really practical. So you have this latency problem with REST, right? If I make an HTTP request for a tiny piece of JSON data, all of a sudden I've got to go all the way around, and that's just to find out, by the way, what the image URL is, and then I make another request to a CDN somewhere and I get that URL. This is stuff that was designed for large, coarse-grained images, documents, images, movies, right? These are the things that you use when you browse. HTTP was never designed to send small, fine-grained pieces of data. As we'll see, that's what web applications do. They deal with large, fine-grained pieces of data. So here's sort of what happened when we started up the Netflix application for a while. This didn't really last. This mechanism of making all these HTTP requests didn't last. We were trying to do the right thing. We were trying to build a RESTful API, but the latency just killed us. So once the web was a place to get things, 10 years ago, that's fundamentally what the web was. And nowadays, the web is a place where we go to do things. It's gone from web pages to web applications. But we're still building on top of a network stack and using idioms that were designed for downloading documents. So web pages serve small amounts of large resources, and web applications, on the other hand, serve large amounts of small resources. And so HTTP and REST really weren't designed for this. So over time, that RESTful API kind of just sort of became a REST-ish API. It wasn't so RESTful anymore. Anybody out there, by the way, who raised their hand and said they had a RESTful API kind of feel this way, that maybe you kind of deviate and drift a little bit, and after a while, well, frankly, it just becomes RPC. Those resources just become procedures that you're calling and passing a bunch of parameters to. And really, you can't cache them anymore because the thing about procedure calls is they're not idempotent. You can't just rely on one resource being cached in HTTP. So we'll take a look at what RPC looks like. I think a lot of web applications eventually gravitate towards this model, where you're basically building a specialized endpoint for every single one of your views, so you can have one request and only one request to the server. And that's understandable. After all, I mean, a lot of us are building for mobile nowadays. We can't afford latency over 3G connections. So what happens with this RPC model? I mean, granted, you get low latency. But what you do also get is tight coupling. Now if I want to change any of my views, I also need to go to the server and change that. That's one of the benefits that REST had. You expose this sort of generic data model, and your views can take whatever resources they want. But in practice, the latency forces us into this pattern of tight coupling. Issue, of course, we get is no cache consistency, right? If a procedure call just returns data, well, then 16 different procedure calls might return overlapping data. And so if we try and rely on HTTP caching, well, it's really tough because two different resources can end up overlapping with the same data. And now you've lost all the benefit of REST and caching in the first place. You can't rely on stale data not making its way into your caches because two different URLs basically are caching the same data. And that's exactly what's not supposed to happen in REST. Every URL is supposed to be a unique identifier. And so if you've built a truly RESTful system, you can count on the fact that two resources won't overlap in the data that they store. So same info, two different URLs there. So what we want is we want the cache consistency and loose coupling of REST, but we want the small message sizes, just the data your view needs, and the low latency of RPC. So how do we get there? That's where Falcor comes in. So what is Falcor? Well, it is effectively, first I'm going to tell you what it's not, it is not a replacement for your database, your MVC framework, or your web server. Falcor is fundamentally middleware. It allows all of these different parts of your stack to communicate more efficiently by effectively introducing a protocol for data interchange that's optimized for the needs of web applications and not web pages. So what Falcor essentially does is it makes it appear as though all the data out there in the cloud is sitting right there in device memory. And by effectively allowing you to take all of your backend data stores and model them as a single JSON resource out there in the cloud. So you take all your databases, all your backend stores. This is how Netflix thinks about our 80 different data stores as one JSON URL. And then, using the client, we create the illusion that all that JSON data, no matter how many gigabytes it is sitting right there on the client. So how do we do it? Fundamentally, we think about Falcor and this data in the cloud. We interact with it as an asynchronous model. So what does that mean? Well, when you click on Netflix and you say load the home page, Netflix makes a request to the server out there. But what it does is it has this proxy to all of that data. That's the asynchronous model. It sees all the data out there in the cloud and interacts with it as if it were an in-memory JSON object. So we request the data for the gallery. But because the model's asynchronous, it can then take that request on demand and forward it on to the cloud. Now, instead of downloading the entire JSON file, we use the query string to retrieve just the portion that the view is requested. Then it gets cached inside of the asynchronous model, just like a web browser caches resources, and before it's returned to the view. So now if we click on a title, for example, and go to the detail page for a movie, that view makes a request to the model, but because the model's got an asynchronous API, it can gather up all the different requests for JSON from that view and send it as a single efficient request to the server. And we grab another fragment of the graph out there in the server and send down just the piece that the view needs. Now, last thing, we go to, say, a related title for House of Cards, and we pull down that data, and the process repeats. Now, the key thing is, as soon as I hit back, well, we make the identical request as in the previous view, except this time, we hit an in-memory JSON cache. Instead of relying on HTTP caching, which, just like HTTP requests, is too coarse-grained, now we're effectively doing REST but for JSON. And so it's very, very fine-grained. Every single individual property in your JSON object is a resource unto itself. And so since this request is sitting in there in cache, this quote-unquote asynchronous request resolves immediately. And we can repeat that process, and as long as we keep asking for data we've requested before, we get it out of cache. So it's like a web browser, but a web browser for your JSON data. So, it's enough PowerPoint presentation. What is it like to actually develop and work with your application? So, Netflix on Falcor. I'm going to do a little mini Netflix on Falcor. We're going to live code it. Wish me luck. It's dangerous to do live coding, so here goes. All right. Can I move this over? Nope. Can you hear me?
Yep.
Feel like a piano player. All right, so what do we see here? Well, every single application starts with a domain model. And this is actually most of the work when you're building a Falcor application, simply designing your domain model. So as you can see here, Netflix is pretty straightforward. By the way, how many Netflix users we got out there? That's what I love to see. So we have a lot of genre lists, right? If you've seen Netflix, you know it's a relatively straightforward model. When you load up the Netflix application, you see a list of genres, horror, thrillers, that type of thing, each of which contains a list of titles. And so it's kind of like a two-dimensional array. In this case, we have an array of genres in our genre list, and each genre contains a list of titles. Everybody see that? So obviously this is a heavily abbreviated Netflix model because we're only containing 2 genre lists, each of which contains only 1 title. In reality, we have something like 40 by 75 normally. But as you can see, we've got 2 of our great Netflix originals here. We have House of Cards and we have Daredevil. So if you're working with JSON data directly, it's pretty straightforward, right? We all know how to take data out of a JSON object. You just do a series of key lookups. So here, I'm going to go ahead and try and run this, and I'm going to look up the name of the first title in the first genre list. Reset my full screen here. Uh-oh. This worked a second ago, I promise. Anybody spot my problem? Let's show source. Show source. Yeah, I am showing source. Nothing. Oh, web server not actually running. All right. Okay, so that was a lot of effort, but now we see House of Cards. By the way, who can see that and who can't see that out there? Does that need to be bigger? I think it does. Whoa! Delayed reaction. A moment, yeah, there we go. Took a little while. I'm going to try this one more time. Plus, plus, plus. And hopefully it'll eventually get there. Okay, does everybody see House of Cards down there on the console? A lot of effort. Who can't see it? We're going to try 2 more pluses. It'll teach me to do video encoding while I'm doing a presentation. There we go. House of Cards. Straightforward, right? So we all know how to work directly with JSON data, but when you're working with a Falcor model, you're effectively working indirectly with this JSON data through this proxy, this Falcor model. As you can see, the API is pretty much the same. When you're working with JSON data, the data is the API, and that's exactly Falcor's API. So I'm going to take this model, and I'm going to wrap it inside of a Falcor model. And I'm going to take this JSON, and I'm going to basically initialize it to be the cache inside of that Falcor model. Earlier, we saw that Falcor model internally contains just a JSON cache. So now, after I've modified this, we're going to find that we have almost identical API. Instead, I'm just going to take this path and pass it directly into Falcor as a string. And the last important change is that Falcor is an asynchronous model, which means that all of our data is going to arrive asynchronously. When you call getValue, it's going to return a promise. So I'm going to try this, and now we are going to write this value that comes asynchronously out of the Falcor model. And we see House of Cards. We see the exact same result, but let's just prove that, in fact, we have different code running here. Right? So it's the code we just wrote. Okay, big deal, right? Obviously, anybody can write an async API that pulls data out of a live JSON object. That's not that big a deal. But there is a big deal which is coming up, and that is one of the big challenges around using JSON. JSON, obviously, ubiquitous, right? Every JavaScript interpreter out there understands JSON. We love sending JSON around and using it to transfer data between applications because it's just so easy. But there's a big downside to JSON. Almost every interesting application's domain model is a graph. And JSON is for trees. So this causes real practical problems. Like, for example, let's say House of Cards is a new release, right, as we can see here. And oops, this should be named something like, oh, I don't know, recently watched. So this might be a message that you get back from the server when you load up Netflix. And let's say, fine, House of Cards seems like a really cool title. I'm going to watch it. Well, the next time you go back and load this message from the server, what you're going to find is a message that looks like this. Right? After you watch House of Cards and reload the next time, what do we see? Well, we see House of Cards twice in the message. Is this a big deal? Yeah. Why is it a big deal? Well, let's take a look. Let's say I really like House of Cards, and gee, I just want to give it an awesome rating. Let's say it's not 5. And I'm going to go ahead, set the rating of this title to 5, and then let's see what that does to my domain model after the fact. So after I've set this value, I'm going to go ahead and I'm going to retrieve the exact same value. Except this time I'm actually just going to go ahead and get all the data in here. And spoiler alert, you can use ranges. So we've got a slightly expanded grammar inside of Falcor. So in addition to just simple JSON paths, you can put things like ranges inside there. So now I'm going to grab the name and rating of the first 2 genre lists. How do I do that? Well, not only can I put it ranges, I can also put multiple keys inside of indexers. So I can ask for the name and the rating of the first 2 titles in the genre list. And that's going to give me back JSON, basically a subset of the JSON document containing only what I asked for. And so now we'll print this out to the console.
Except your model is already inconsistent.
What's that, sorry?
Your model is already inconsistent.
It's already inconsistent? Why is that?
You have 3 and 5.
Oh, you're right. Thank you. Let's pretend it came down like that. Which it would, of course, from the server, right? Because the reality is, inside of the database, if you've done your job right, there is only one instance of House of Cards. And so when it's going over the wire, you'll expect it to expand when we go from a graph to a tree into 2 instances. So it'll be basically a clone of the same thing. So here, I'm going to print out the contents of this after I do set value. All right, wish me luck, people. Run it. Yeah. Right? And we can see that I got back the subset of the JSON object that I asked for after the set operation, and as we can see, it is inconsistent. Right? I've tried to set House of Cards, but because my graph got expanded into a tree and I had duplicates, now I have an inconsistent cache. And that is definitely not something that we want. It's a really painful problem in applications, trying to keep a consistent cache, especially when we have to use JSON as our interchange format. So what's the solution? Well, actually, an engineer at Netscape actually said something, it's a maxim I think is true, which is that there are only 2 hard problems in computer science. Anybody heard this before? Cache invalidation and naming things. Those are the 2 hard problems in computer science. So this is an exceptionally hard problem. Well, one way is you can try and go through the entire model and find all the same instances of objects. Typically when servers take your graph data and they convert it into trees, they use the duplicate and identify strategy. So in order to solve this, they attach IDs to each title. So here, when the message comes over from the server, it's likely to have something like this. Right? How many people out there use this strategy? I'm guessing pretty much everyone if you're having to send this over and require cache consistency. So in Falcor, we've introduced a graph modeling format for JSON. So it's a way to model your graphs in JSON so that you never have to create duplicates and then dedupe them when you're merging them into your cache, which is what most people do. They examine the ID, and then where 2 IDs are the same, they do duplicate when they put it into the cache. Well, what's easier than deduping is never making copies in the first place. So what we've introduced in Falcor is the notion of a reference in JSON. So a reference is a special value that we've added to JSON. And the first thing I'm going to do here is I'm going to take every single item with an ID, and I'm going to make a symbol top-level map for all of the titles by ID. And I'm going to organize it by, well, ID. So now I'm going to copy this title So this is the two-step process to go from JSON to JSON graph. I'm going to copy this title into this one location. And now I'm going to go to every other instance in the JSON document where House of Cards exists, and I'm going to replace it with a reference to that one and only one location in the document. So I'm just using a simple JSON path here. Not especially high tech here, right? JSON graph is a very, very simple format. Now under the hood, ref is just going to create a simple object that looks like this. That's all this little function does, by the way, and parses the path into this little array of keys. So that's all that's really going on under the hood. Now, the model knows how to deal with JSON graph. So I'm going to go back, and I'm going to rerun this exact same program. Whenever Falcor comes across a reference while evaluating a path, it jumps to the root, follows that reference until it arrives at the destination. So if I rerun this, we see we have only one value in the cache, and therefore, total cache consistency. If I set rating on that item, no matter where it is in the JSON, that rating propagates everywhere, because we've only ever got one copy. Now, this isn't just in the cache, it's also what gets sent over the wire. So you avoid duplicates ever being created. So that's relatively straightforward. So one of the things Falcor does for you, in addition to basically being the entire API, basically being your data model, it gives you total flexibility around where your data lives. And that's really the power of the asynchronous API. It means that here, obviously, I'm working with data in an in-memory cache. But it turns out, and this is often what we'll do, we'll work with data in an in-memory cache, a mock of our server. And then later on, when the server gets written, we will completely take the data out of the in-memory cache, but change no other code. Because all of the code for working with remote and local data in Falcor is exactly the same. So, to prove that, I've got a little node server running right now, and I'm just going to go copy, I'm going to cut this entire model. So we're going to take it entirely out of the client, and we're going to move over to this node server, and we are going to paste it. Right? No cheating. I just cut and paste, and now we're running inside of a node server. So I'm almost done. I'm almost ready to execute the exact same code that I ran before. But first, I've got to have some model, obviously, on the client side to request data. So I'm going to create another model, but this time, instead of initializing the cache locally, I'm going to give it a source. A source is effectively a data source. Every model uses a data source to retrieve its JSON information. And a data source is nothing but an interface. You can have all sorts of implementations of the data source interface. This particular implementation proxies any requests made to the model out there onto the server where it's going to be evaluated on the model, which is now running in memory on our node server. So I'm going to put in new Falcor HTTP data source, and we're going to put in this model.json. So now we've got a single URL where all of that data out there in the cloud is going to be exposed to us. And I'm going to simplify this. We're going to forget about the set stuff for now. And just go ahead and try and retrieve, say, the name of the first genre list. So we'll get value, and we'll print the name. So now, obviously, we've got no data whatsoever here on the client, so if we get any data back, it's got to be coming from the server. So let me just double check that everything's cool in the server. So the way the server works, what you're seeing here is nothing but a standard Express server. We got any Express users out there? Node Express users? Yeah, pretty popular MVC framework. So as you can see, all the magic is right here. We are using what's called a data source route. Now, a model with an in-memory cache actually can be made to adapted to this data source interface. So effectively, when you're talking to the HTTP data source, all you're doing is proxying the information over HTTP, and then it's being executed against another data source. And because model can be adapted to the data source interface, all we're doing here is we're basically exposing all of the data inside the cache of this model at this one URL, just using some Express middleware. So I save. I'm going to just make sure to rerun my server. It's a real gotcha when you're doing live coding. And we run. And we see new releases. So as we can see, we have the exact same model for working with local data as we do have for working with remote data. So, OK, fine. Not everybody runs with Node and stores all of their data in memory on a Node instance. Probably not a very good idea, right? In practice, we want to store our data in back-end services like databases, MongoDB, and the like. And so the last piece here, am I completely out of time? Am I just, oh great. So the last piece here is how we go from a real JSON model out there on the server, on the application server, to a virtual JSON model. So how do we basically make it appear as though all these different data sources are one JSON file on the application server, when in fact, that application server is completely stateless? Well, we use a router. Now, most of you probably who have any Node or application server experience know what a router is. It's a relatively straightforward concept. When you go to Amazon.com and it says, hello, and says your name, it's not really because they have an HTML file that's statically stored for every single one of their users on the application server, right? What's going on is a little bit of trickery. They have, very likely, some pattern that matches certain types of URLs. And when a URL request comes in that matches that pattern, they go off to the back-end service, get your data out of the database, and generate an HTML file and display it to you. Now, in our world, we have only one URL. By the way, why do we have only one URL? It's to get around the inefficiency of HTTP, right? I don't want to be able to have to make 100 HTTP requests to get my data. I want to be able to get as much or as little of the graph as I want in a single HTTP request. And so by putting all of our data behind a single HTTP request, we get around the built-in inefficiency of HTTP. We can ask for as much or as little as we want in that round trip. So going back to this idea of a router, we only have one URL here. It's that model/JSON that you saw earlier. In fact, if we take a look at this request, we can see what it looks like. We get back a little fragment of JSON graph. I don't know if you can see that. So basically just the data that we asked for, the fragment of the JSON graph out there on the server. And if we take a close look at the headers, we can see that all that happened is we passed the requested path out there on the server. So relatively straightforward interface. But what's going on here, because we only have one URL, we're obviously not matching against URL. What we're doing is we've built a router over JSON paths. So, right now, genre list zero name is just being evaluated in memory against the model. But I'm about to show you how I can build a router that actually matches JSON paths, just the same way you build a router that matches URL patterns. We're going to look for patterns in the paths that come in, and we're going to go off to the database and create just that subset of the JSON document, the model requested by the client. So let's take a look. It looks very, very much like creating an express route. So we have an example of that right here. I've created an express route, as you can see right here. This is how you create a route in Express. You can sort of specify a URL pattern and then a piece of code that runs to serve it. Now, in this case, I'm using this Falcor server middleware to proxy any data in the data source over. But you know, in Express, you can put in things like patterns and match all sorts of patterns of URL and dynamically generate the data. So I'm going to remove this in-memory model, right? Because nobody wants their memory stored inside of a Node instance. You want your data in a database, right? And I'm going to paste in an instance of a router. So let's take a close look at this router. A router matches patterns in JSON paths. So here I'm looking for every possible path where it's genre list, and then some index, and then the name. By doing this, I'm effectively going to virtualize, make a little basically simulate the location in the JSON document of the name of our various genre lists, whether they be horror, thrillers, etc. There's no actual data in memory, but as you can see, as soon as I capture a request for this path, it gets put into this path set, because remember, when you're going to Falcor, you can ask for as many paths as you want in a single HTTP request. And so somebody might ask for the first 15, the names of the first 15 genre lists. So within one route, we might actually match multiple JSON paths. And then I'm going to go off to this back-end Netflix service where we've got, it's much more like a REST service where we have a bunch of data, all that genre list data that we don't want to send all the way over to the client. We only want to send the small subset that the client actually wants. So if we were to look at this actual request right here in a web browser, we would see it's a nice, big, chunky request, the type of request that you would see in a REST server, for example. That's a lot of data. But I want to give the client the ability to ask for just the tiny bit of data that they want. So we are going to match requests for names of genre lists. And all we're going to do is we are going to create an individual path and value combination for every single one of the paths that this particular route matched. So if you came in on this client side and you asked for genre list 0 to 5 name, well, that would all get captured in this one path set. We would match all those paths in this one particular route. And that allows us to be much more efficient when we go to the back-end service. We want to grab as much data as possible when we make that round trip. And so path set here, once matched, if I pass that in, would look like this. It would look like a parse version of that. Nice little, just an array of keys that we can analyze. In this case, we're using indices, so it shows up as a array. And our job is to basically return the JSON graph subset of the document out there in the cloud that contains just this data. And so on and so forth, one, yada, yada, yada. Now, one way of doing that is to build this little JSON graph subset. Another way of expressing this is to have a path and value combination, and it turns out to be more ergonomic in many cases, for every single one of these values. And 5 more of those. And so we're going to use a promise of an array of these, a promise of an array of path value. So that's the logic that you're seeing executed here. We make this call, we get that top-level array of genre lists. We loop through all of the requested indices. You can see here I'm matching integers, and then I'm assigning it an alias of indices. So it's going to be like 0, 1, 2 in an array. And then for each one, I create this path and value combination. And now under the hood, the router just takes all those paths and values, mixes them into a single JSON graph response. So now that we have this, instead of returning our model as data source, it turns out that our router also implements the data source interface. So you can connect a model directly to a router. Typically, you go over the wire and proxy it through an HTTP server. So I'll run this, and we rerun the old HTTP server. And now let's change our query here on the HTML side to look for, oh, great, it's already asking for the first name. So if we run this, hopefully, we're going to see live data. Whoops. All right, pay no attention to the man behind the curtain here. What went wrong? What went wrong? I'm going to need another group code review from you guys. I create my router, return my router.
Do you want router to be the argument to data source route instead of the function and then returning router?
No, part of the reason we want to pass this function in is so that we can create the router and have it have access to the incoming request and response information. So we might want to consider that inside of our route. So it's actually totally legit. That's working code. Let me see if I can run this in a good old debugger here. Luckily, I have this already up and running. I will launch. By the way, who out there has tried Visual Studio Code? Yeah, pretty cool new free program, by the way, for those who are getting into node debugging. So now if we make our request, I should hit that breakpoint.
You're not supposed to pass the request to the router. You're just returning router.
Yeah, it doesn't actually need the request because it's just going, it's not using any of the parameters inside the request. But that's a good guess. Thank you, Ben. Localhost 9090. All right, we'll give that a few more seconds. These are the risks of live coding.
Wait, how does it get any of those parameters?
Pardon me?
How does it get any parameters out of the request?
I'm saying in this particular instance, I'm not using any parameters on the request, so I wouldn't pass them in. But, pardon me? The query, like the query string that you saw earlier?
The path, yes.
That's all handled here by the data source route. So effectively, this data source route is executing this function, and it's getting back the router, which is a data source that has these get set operations, and then it's parsing the path out of the URL, issuing the get to the router, and then returning with the response. So how much time do I have? I'm done. Well, I tried. You're going to have to take my word for it. That in fact, what will happen when this works correctly is that we'll go back to a back-end service and realize that data and just that subset of the data out there in the cloud that I asked for on demand. Yep. Good question. So I think we're actually driving it very, very soon at a release. Now, I want to take full responsibility for this. I've been saying that for many, many months. But this time I actually think it's true. There's a lot to do when you're kind of reinventing the way people do data access. It's a pretty hard and broad problem. But I'm feeling pretty confident that we should see a release sometime in the next 2 to 3 week time frame. Yep.
So is this very much like clients, this sort of clients in the first server, and then everything that kind of happens beyond that is regular MongoDB or Postgres or whatever queries? Is that sort of a translation layer, or are we...
Anything goes once you get to the server, right? I mean, really what Falcor is about is it's about primarily optimizing that last, all-critical jump to the client. We want 3 degrees of data freedom, effectively. We want you to be able to request as much data as you want in a single response. We want to be able to push you that data whenever it arrives, that's the asynchronous part, and we want that data to be able to live wherever you want it to live. So this is about creating a protocol. One way of thinking of it is effectively REST for JSON, right? When we do these GET calls over paths, it's just JSON paths instead of URL paths, but all the same RESTful principles about idempotence and cacheability hold true. So we're trying to build a protocol. Fundamentally, it's a protocol and a series of utilities for that protocol for transferring JSON data from client to server efficiently. Yep?
So your example, where did the indices variable come from?
The indices variable, you're at right here. So notice here I'm giving the pattern an alias, and that effectively inserts it onto this path set as a property, and that's where it came from.
Property of the path.
Yes. So the path set is just the parsed path, but then if you give aliases to the individual keys, they get tacked on there. So then you don't have to reference things by index, and you can reference them by alias.